can probably start. Maybe if everybody who's having a conversation could continue the conversation outside, and everybody who wants to listen to the talk come in, that would be great. Okay, so today we're going to go a little bit deeper into a specific family of models, namely latent variable models, and how to scale them. So what we did yesterday was we looked at the parameter server, how to distribute variables in this context, and how to optimize accordingly. On Monday, we covered, actually whole places where big data arises. Today, we're going to look at a specific family of models, namely latent variable models, and we'll look at how to actually do inference in them. Now, given that we didn't really cover a lot of latent variable models so far in the summer school yet, we'll actually start off very gently with clustering. Okay. Who has heard of clustering before? Okay, great. Who has seen that kind of diagrams before? Okay, that's about half the audience. Okay, who knows what a for loop is? Okay, great. This is a for loop in statistics. Okay, so let me explain a little bit more detail what I mean by that. So what we have here are some data, the xi's, and I'm assuming that, well, they are drawn according to maybe some distribution from some cluster. In other words, I have some cluster IDs zi. So for instance, this could be, if I wanted to, deal with colors, they could be, red, green, blue, whatever, maybe pink, purple, yellow, anything that I'd want. And so I first go and say, let's decide, okay, well, I want to pick some color. So I pick a zi equals red. And then I'll pick a specific hue of red. And maybe, there's like a favorite red color, and then there's some things slightly around it. So let's say, for instance, I'm outside and there's a field of poppies and corn. Then, the red is going to be a very much poppy-like red. Okay. And so now the mean and variance, basically, how much that color varies, would be specified by, let's say, mu j, so j being red, would be, the mean for red, and then maybe I have also a variance. And I would probably also want to specify, if I have a field of poppies, that maybe there are only a few poppies and there's a lot of field, so there'll be a lot more green than red, and that's about that. So now, what do those circles mean, and why are some shaded and why are some not? Well, shaded circles typically mean that these are random variables that are being observed. Hollow circles mean we don't observe it. Now, the last thing is, the second last thing is those arrows. And the arrows basically allow us, so this is what's called a directed graphical model, and you can do similar things also for undirected graphical models. Basically, they tell us a dependence of what depends on what. So, for instance, I could go and decide, okay, I'm going to pick red. So, having chosen red, well, xi, namely the color that I observe, depends on the fact that I decide, okay, it's going to be red. And furthermore, it also depends on, the distribution of, red dots. So that's, the left circle. And those two jointly then allow me to draw xi. The unfortunate thing is, however, that I only observe xi rather than mu and z. So I'll have to do something to actually infer them. Now, of course, it's not just a single, red, blot that I observe, but there's actually a lot of them. In particular, I observe m of those. So that's why I have this box around here, and it says I going from 1 to m, which is this. So rather than, drawing m circles, which kind of gets old really quick, I just say, well, repeat. Ditto, I say, well, for k clusters, so I'm assuming that I have maybe k different colors, I'm going to, have k different means and variances to get everything working. So that is essentially the reason why you use plates. Plates are quite powerful. They let you actually specify most graphical models, but not necessarily all of them perfectly. But for the ones where it actually lets you represent them well, they're really useful. Okay. So this is mixture of Gaussian clustering. Everybody should know that at some point. Okay. Now, what's the problem if we actually want to do this at scale? Well, okay, so let's just look at it. Well, the problem is that, the means and variances, if I have, images on different machines, well, they're actually all shared. So this is actually a global state. And if I knew the prevalence of, the colors and, what their corresponding distribution would be, if I just had that correct number on all the machines, that's all I would need to do to solve things locally. So then the data is just purely local. It sits on individual machines. And then, for each individual pixel, well, I need to know what the local state is, basically, which cluster it belongs to. And if I just knew this accurately, then I wouldn't even have to share the rest, which would be kind of nice, but here's a few issues. So quite often, not in the context of clustering images, pixels, but for instance, when you deal with text and so on, and you build topic models, which are a little bit fancier, then this global state is actually way too big for a single machine. So what this means is that quite often I won't even be able to hold all of this in main memory. Maybe I can keep some of it if I actually cache it on disk, but I can't really keep it in memory. So that's a bit of an issue. However, I'm making the working assumption, and this need not always be true, but I'm just going to make my life easier, and you can sort of kind of engineer around it, namely that all that a machine needs to know about its own data is what it can keep in memory. Right? So back to the example of yesterday where we had the English and the French and the Spanish documents, that basically the machine processing the English documents would at least be able to hold its English language model in memory, but it wouldn't necessarily have to be an expert in Spanish and French in order to do a good job for English. It would only have to know that possibly there are some words that are related. Okay. The second thing is, the data itself is huge. After all, we're talking about big data, so there's no hope you can keep this in memory. There's no hope you can keep it on a single disk. This actually has to be distributed over several machines. Last, and this is actually what comes to our rescue, I have a whole bunch of variables that are just locally relevant, and I don't actually need to know those. I don't need to know, for instance, how I went to annotate each English document in particular to deal with the French and the Spanish ones, but maybe I only need to know that in the context of some summary statistics. Now you might say, well, clustering is kind of really contrived, but don't worry, we'll go through the entire thing in the context of clustering because it's just the really easiest model to think of. But there are some more fancy models where the same thing also applies. So it looks very similar to what I showed you before, but now the graph gets a lot bigger and messier. This is actually a model we're going to look at shortly afterwards. It's called latent Dirichlet allocation. And so there you have a mixture of topics in a document. And I'll actually explain in a bit more detail what the difference is between topics and clusters, because people consistently confuse them. Very smart people consistently confuse them. And basically, if you can think of it this way, okay, well, you can maybe cluster me with, other maybe CMU professors who have very similar interests to me, but maybe it's a better way to describe my interests as, okay, well, maybe I care about classical music, and I care about machine learning, and I care about a whole bunch of other things. And so this way, you can think of these as almost like principal components or primary colors by which you can represent the user's interests. So this is actually why these models are really very popular for the internet, rather than having a lot of clusters. Because even if I assumed that I had 1,000 topics and I could only pick 2 out of 1,000, then you can immediately see that you can get something of 500,000 different pairwise combinations, where otherwise I need to create 500,000 clusters, which are usually not very understandable. So don't worry about the details here. We'll go into this in a lot more detail later on. But the only thing that's relevant to know here is these are basically documents. These are the words in the document. And what I now have is a global language model about what the topics look like. And I have a global model of their prevalence. And this is enough in order to fully specify and synchronize models. What I have locally is basically an annotation of each word in terms of which topic it belongs to. And so basically this is the local state, this is local data, and there's a global part to be synchronized. Now, that sounds a little bit more involved, but it's still quite straightforward. What you do in reality is actually you assume that you have a time series because users' interests change over time. So it's basically this model. But now repeated over time, I get an entire chain. The same argument still goes through. So this is actually what's called temporal LDA. And you can read up in some papers that we wrote. So really don't worry about the very specific details. But what you can see is that you can very quickly design much more complex, much more involved models that describe random variables and how they interact. Yes, you actually have to do some work to then design an efficient inference algorithm. But as long as you can set it up in such a way that you have local state, and that one can potentially be quite big, and data, that is also potentially quite big, but it's still local, and then a global state that is small enough that it at least that its relevant view can be kept in memory on each machine, then you actually can do inference quite efficiently. So, yeah, as said, we'll discuss that model in a bit more detail later on. So now how can you actually address the issues that I brought up? So the first thing is that the local state is way too large. So basically, those variables state I don't really fit into memory. But the good thing is they don't really have to, because, well, if I need to know what a particular document does or what a particular image does, I can just as well load that local state back into memory when I load the document into memory. Then I do something with it. I maybe update my estimate of that state, and I dump it back to disk, and I move on. So I'm basically just streaming this from disk, edit a small amount of it, and then just write it out, and there is not much penalty relative to storing it in memory. Okay. The second thing is that I need to actually deal with the fact that the global state is too large for possibly a single machine, and it doesn't fit into memory entirely. So I keep a local view, and I synchronize this between local and global appropriately. So let's just go through it. That's not what I wanted. So you basically stream from disk. You go and asynchronously synchronize between what each individual machine does and what you do globally. We'll look into that in a lot more detail in the next few slides, but basically suffice it to say, when you perform local updates, subject to some interesting caching that we are going to go into, I'm going to synchronize that with the consensus view. And then furthermore, as I already hinted at, we only need a partial view on each machine. Keep in mind that you should never ever treat a multi-threaded machine with, let's say, 16 threads as 16 separate machines. That is extremely dumb, but do not do this. And unfortunately, I've seen a lot of implementations where people do this. This is just horrible. It's bad. Because it basically trashes the memory interface, and you're making things so much worse. It's very, very poor design. Just don't even think about it. So basically, what you really want to do is, within multiple threads, they share the same view of the parameters, and then that is being synchronized. So there's actually a really nice library that lets you do multi-threading without too much pain. It's called the Intel Threading Building Blocks, or TBB. So rather than dealing with pthreads or OpenMP or anything else, just take Intel TBB. It's probably the nicest multi-threading library you can currently find. It's all open source and free and whatever, so you can use it for your commercial projects if you want. And it's probably the least insane way of doing multi-threading. It gives you a lot of things for free that otherwise are really hard to deal with, so just remember that. Yeah. It has some interesting quirks about Intel versus AMD, about some atomic variables, but you probably won't need them anyway, so it'll just work fine. Okay. So let's actually look at what this looks like in practice. So what I'm going to do is I'm basically going to perform Gibbs sampling. And I'll explain Gibbs sampling in a little bit more detail afterwards. So what we saw so far is a lot of inference algorithms that use optimization to get to the value of the parameters. Actually, can I borrow a notepad from somebody? A notepad and a pen. Or actually, actually, if I can, sorry, let me get it from my backpack. So we can just. Okay, so if you recall, when you perform inference, and you have, a probabilistic representation, then so suppose I end up with some, I have some data, x, and I want to estimate a model p of theta given x. Right. Wow, the white balance is highly adaptive and my hand is way too dark. Didn't know I had such a black hand. Okay. It's good if you have those nice adaptive algorithms. Yeah, sorry about that. So, what you can do, and this is something that we saw quite a bit before, we can optimize. Because what we basically had is, remember, we have basically p of x given theta times p of theta. So remember, this was, of course, nothing else than p of theta given x times p of x. So I'm just re-deriving Bayes' rule here. So we get, of course, p of theta given x is p of x given theta times p of theta over p of x. And of course, this guy is constant, so you can just ignore it, and we get a proportional term. This is Bayes' rule. And so if we looked at, theta, then one way to capture what's going on in this probability distribution is just to look for the mode. And this is great as long as we have this, which, for instance, is guaranteed by log concavity. But if it went on like so, then maybe just getting the mode might not be so great. So, for instance, if this was the cost of a project, and there's a chance that, well, it might cost more than twice, then just looking for the typical cost and using that as the only reference is not a good idea. So, for instance, when you organize a summer school, you don't just want to look for the typical cost, you also want to make sure you don't completely bankrupt yourself if something really bad happens. Okay. So, therefore, optimization may be a good idea, but sometimes you want to have something a little bit, more accurate relative to the probability distribution. So what you could do is you could, for instance, go and draw from p of theta given x. This is sampling. And then, well, what you could do is, for instance, you could just compute, the estimate of the budget of theta. We draw these of theta I. And then I would see, what the budget really would look like. And that would give me a better idea of, whether, for instance, we should increase the fees, or maybe we should, close the registration, or maybe, we run out of space, or whatever else. But basically, this might give me a better idea of what the situation might look like in reality. Okay. Unfortunately, in most cases, actually performing this operation here is really difficult, and you can't just do it easily. Because maybe sometimes this parameter is very, very high dimensional. So, for instance, for a topic model, you might have 100 billion, maybe 1 trillion parameters of that form. So good luck sampling from all of them at once. You just can't. In some cases, you might have a lot fewer parameters, but it's still intractable because that probability distribution, basically nobody's implemented an algorithm to sample. If you have a Gaussian, sure, you basically invoke GSL and you use it to sample or a Poisson, whatever. So, somebody has coded this up for you. But in general, people haven't coded up your specific problem. So then the question is, how can you sample from this, even if that's not the case? So there's a lot of really beautiful math that can be done, and actually Nando's written a couple of very seminal papers about this. But essentially, this gets us to the area of Markov chain Monte Carlo methods, for instance, and particle filters and a lot of other things, which I don't have time to go into a lot of detail here. So if you've never heard about MCMC, or, for instance, Metropolis Hastings, or particle filters, I suggest that very strongly that you Google for this term, and you'll probably find a very nice Wikipedia page with a lot of links to it. And you should actually read up on this. These are very, very useful techniques, not just for statistical analysis, but also, for instance, for existence proofs and similar things and complexity results in theoretical computer science. So the methods are way more applicable than just probability. As a matter of fact, I mean, this was used when they designed, the atomic bomb. So, yeah, you can do a lot of not so constructive things with it. Okay, and then there's particle filters. Sometimes it's also called SMC, sequential Monte Carlo. Okay, now this would be quite easily an entire class in its own right, so we are not going to bother about this here. Instead, I'm going to show you a very simple, very specific way of doing the sampling. And this is called Gibbs sampling. And, okay, it's actually a special case of what I showed you before. And it's like a super simple idea. Suppose I have some really complex, ugly beast of a probability distribution, P of x1 through xn. Well, maybe P of x1 given x minus 1, so that's basically everything else, maybe that is really easy.
Alex?
Yes?
Can you move the paper a little bit down? We don't see the first.
Oh, yeah. Okay, now we see Gibbs sampling. Right. Good idea. Yeah. Actually, I should probably just control it on my own screen. It has a feature here. So basically, maybe this is really easy to do. So for instance, if all the xi's are binary random variables, so they take only values 0 and 1, then I can just go and fix all the other ones and evaluate this quantity here for 0 and for 1. I then normalize such that the probabilities add up to 1, and then I draw from it. By the way, who knows how to draw from a biased coin? Who knows how to do that? Okay, I guess some people are too embarrassed even to say, yes, I know. It's actually really easy. So let me just give you the idea. So here's 0, here's 1. And I invoke randu, which basically gives me a uniform random number between 0 and 1. And if I want to make sure that this succeeds with maybe 0.3 probability, then all I do is I just accept. Then I basically say, well, hey, 1 happens in this case, and 0 happens in this case. Basically, if that random variable psi is greater than 0.3, then I emit 0. If it's less than 0.3, I emit 1. Okay. So this is how you can draw from a biased coin. Okay. Now, I can do the same thing here, maybe for x1. And I keep everything else fixed. Then I go on and draw P of x2 given x minus 2. So I've just updated this. And I do that up to P of xn given x minus n. And then I repeat this. Okay. So in doing so, I can, after just waiting for long enough, and that long enough is with the footnote of, well, ask your friendly statistician to prove a theorem for it, and he might have some not so friendly words for you back. So basically, proving convergence rates for these algorithms is sometimes the really tricky part. The good thing is the implementation is really easy. And to get started, you just care mostly about the implementation. Basically, what it means is that if I go through my random variables one at a time, and you don't only have to take one at a time, you could, for instance, take pairs at a time, then you will get an algorithm that very efficiently eventually will draw a sample from that distribution. So you could say, well, okay, well, let's say I wait 1,000 steps, and then I get a sample. What about the sample that I get at 1,001 steps? Does somebody have any idea of what can be said about the sample at 1,001 steps relative to the one at 1,000 steps? Okay, any ideas? Somebody already mentioned, said the magic word. Yes, so they are going to be correlated because, well, I only basically performed one Gibbs sampling step. Great. However, they're also drawn from the same distribution. So what actually happens is that now we basically get samples that are, yes, correlated, because I mean this is now a Markov chain, but they are drawn from the same stationary distribution, namely the correct distribution P of x. In some cases, it may be perfectly okay to take the samples that are drawn from the chain and use each and every one of them if I don't explicitly take advantage of the fact that they are in the order at which they occur. But what it also means is that in order to have another sufficiently independent sample from what I saw so far, I need to wait for long enough until it's mixed again. Right? So that's the one thing to be careful about. So if I basically want to have the equivalent of a sample average over maybe 10 terms, then I need to, again, run it for long enough until I've mixed, and then I run it again for long enough until I've mixed. There's something special about the first part of the sampler, because if I was able to, pick a set of variable assignments here that is typical for the probability distribution, well, I wouldn't have to go through all of this pain anyway. So I have to do something that's often called burn-in. Basically, I have to wait until my sampler has actually converged to typical samples from the distribution that I'm interested in. So for instance, in the clustering context, it means I have to wait until my cluster distribution, which is what we're going to have fun with in a moment, has actually converged to something where it captures, the right document top, clusters or, the right colors, and that may take a while. So in many cases, you only want to have, a single sample from, the typical distribution. So you basically wait until you've burned in and then take one guy. In some cases, you keep on going. Can somebody tell me why, if I use clustering, and I keep on sampling and I keep on going and going and going, things can actually go horribly wrong? So I have to add to that. I'm going to assume that we'll only have, let's say, I'm only going to give you 100 clusters, and I'm going to sample, and at some point I get my first sample, and I keep on going for long enough until I've properly mixed again. What could possibly go horribly wrong if I did this? And I just average over those terms. It's a slightly tricky question. Okay, let me give you a hint. Is there anything special to the red cluster being cluster ID number 42? No, right? There's nothing special about that. In other words, I have a permutation invariance in my representation of, which cluster has which cluster ID. And so if I afterwards go and actually average, over all the things that cluster 42 could look like, I will get everything nicely smeared out again. So basically, what I ended up doing is I ended up adding another parameterization to my problem, which actually kind of obscures some of the interesting things because I care less about the red cluster being cluster number 42, but about the red cluster being red. So I would actually need to be very careful and factor this out. In some cases, adding those things can actually make your sampler a lot easier to implement and make it mix faster and do a lot of other things quite nicely. So for instance, in the hierarchical pit manure process, doing things of that form gives you a very, very nice sampling arrangement. So there's a nice paper by Buntine et al. I think it's around 2012. And if you like delving into the intricacies of samplers, this is probably a place where you want to look. It's a cool paper. Okay. Now, back to this, right? So what I'm basically going to do here is I'm going to use a Gibbs sampler which will resample the cluster IDs. It'll basically resample ZIs. And then occasionally I'll go and resample the means and variances and so on. Well, actually, as it turns out, you can integrate out some of the global terms, and then I just have to deal with sufficient statistics. But this is actually quite a bit beyond the scope of this class. So basically, there is a trick how you can deal with these terms here implicitly. And the only thing you really care about is the data and the cluster IDs. And then you need to synchronize some parameters, which are just functions of these two terms between machines. But it basically means I go and resample one cluster ID at a time. And now I'm going to make an approximation. And it's quite a severe approximation, except that it's actually fairly benign in the big data scenario. So don't try this with 10,000 samples, because the algorithm will fail miserably. Try it with 10 million, a billion samples, and it'll actually work very nicely. And the idea is basically that I can locally on each machine pretend like this machine was the entire universe, and I can just incorporate changes from global as they come along. And the idea is that any local change is only going to be of limited scope relative to what globally happens. Okay, so this is in a little bit more math. So if I assume that, for my mixture of Gaussians, I have a multinomial distribution with the Dirichlet for cluster ID, and if you've not seen a Dirichlet, don't worry about it. Basically, this is really just a convenient way of saying, well, hey, we have something that's very nicely compatible with a multinomial. This is actually called a conjugate. But basically what it means is that if I get rid of this multinomial distribution, I can directly write out the probability that Zi equals Z, given everything else, is given by the number of times I've seen, cluster C before, when ignoring this ith sample, plus some smoother, divided by total count minus 1, plus the sum of the smoothers. Okay. Who has heard about Laplace smoothing before? Okay. Who has ever implemented something like a document classifier, and you used word counts and logs, and then in order to make sure that the logs didn't produce something like log of 0, you just added 1 to all the counts to make the problem go away? Who's done that? Okay. Congratulations. You just implemented something that Monsieur Laplace suggested 100 years ago. This is Laplace smoothing. So there's actually a very nice theoretical basis. This is exactly what's happening here. We're basically taking the counts, adding a small constant to it, and then you just need to normalize suitably. Except that rather than adding 1, you can add something else to it as well. Right? This basically prevents a cluster from ever having 0 probability and dying entirely. There are much more sophisticated ways of doing this, and this leads to what's called Bayesian nonparametrics, but we're not going to go into much detail here. So there's something called the pit manure process, the Chinese restaurant process. There's a lot fancier tools that you could use, but we'll use something very primitive. But the interesting thing that you can see here is that if I have several machines, the only thing that I really care about is just how many times cluster Z has been picked in total. So this is the only statistic that I need to synchronize between different machines in order to know how popular a cluster is. I don't need to know which cluster specifically was selected for which document. I only need to know this in total. So that's this quantity here. Now it turns out that for Gaussians with the Gauss-Wishart prior, you can use exactly the same argument. And actually we all know this, right? Because if we want to estimate a Gaussian, all we need to do is we need to estimate the mean and the variance. Has anybody of you ever been mystified when you use the pocket calculator? Okay, maybe you're probably too young for that, but basically with a statistics mode, and you would add numbers into it. And how on earth did it do it in the end that it really got the means and the variances exactly right on the spot without, working out any other details? Well, okay, I was mystified, but that's probably just me playing with this before I knew math. So here's what's really happening, right? We know that the mean, mu, is basically 1 over m, sum over I going from 1 to m xi. And we know that the variance, basically sigma squared, is, well, 1 over m. I'm not going to worry about the m minus 1 versus m discussion here. I equals 1 to m xi minus mu at squared. Right? Now, we also know that we can write this out as 1 over m sum over I equals 1 to m xi squared minus 1 over m sum over I equals 1 to m xi squared. Right? Now, what this actually tells us is that these two quantities here are the key quantities that I need to communicate. So the sums over the xi's and the sums over the xi squared. There's actually a third key quantity that I need to communicate, and that's m. Right? Now, if you squint hard, you'll see those three here. Right? That sum over all the, documents that go into a particular cluster, that gives me that count. That gives me the corresponding unnormalized mean, and this gives me the unnormalized second order moment. So now all I have to do is invoke algebra to obtain these things. Next week, Animanan Kumar is going to push this a lot further when she talks about spectral methods. Basically, you can find such algebraic conditions for way more exciting and sophisticated models, and she'll give a great lecture about that. Okay, but here we'll just play dumb and we'll just use, variances here and means. But basically, what it means again is we only really need to synchronize a very, very simple thing, and I don't have to know about any specific document or any specific color what it does. I just need to actually keep things in sync. And this leads to the following algorithm. I basically have global variables that are being stored on the parameter server. I have local replicas, but only for the clusters that I need to know about. So I have one copy per machine. And then I basically, per machine, treat this as if it was the entire graphical model, and I just keep things in sync between global and local. So this is very similar to what we saw in the past 2 days when we looked at distributed optimization, for instance, what Mu was talking about. The good thing is that I now, with the slight approximation of, well, independence rate isn't quite true, but it's sufficiently close, I basically don't have to do any logs. I basically, run my algorithm quite as I would have on each single machine and keep things in sync. This is also great for prototyping because you can basically develop on a single machine, make sure it's really efficient with multi-threading and everything, and then you put everything else on top of it. By the way, the slides will be available, so you don't have to take pictures of the slides. So in LDA, you can, well, basically, rather than just those cluster means, these will be actually the topic word counts. And we'll get to topic models shortly. So let's just have a look at what happens here. So this is basically where the global variable sits. This sits on the parameter server, and then each of the clients have some of the replicas. Now, suppose I have a slightly more interesting network structure. And this is, I think, not the horrible approximation of what once upon a time used to be Yahoo's network structure. So compare that to what Mood talked about yesterday when you saw this very nice picture of basically things like a cloth network or butterfly networks. This is heavily oversubscribed here. Basically, the poor switch up here has to do a lot more work than the top of rack switch, which then connects all the machines. So what you could actually do, in case you were really constrained to have to deal with such an architecture, you can actually have a hierarchical synchronization procedure between this. I would, however, strongly urge you to talk to your friendly systems administrator and tell them to clean up their mess, because this is really not acceptable anymore in 2014. In 2004, yeah, this was a reasonable architecture, not now. So the relevant paper to look at is a paper about telephone switches, and it's by a guy called Kloss, or Clo, whatever. Not quite sure whether he's French or French-Canadian or Canadian or whatever. But it's basically, this was published at AT&T Bell Labs. You actually can find a link to his paper on the Wikipedia page. So basically, here's the problem that they started out solving. So this is in the old times when they had mechanical phone switches. And so you can basically have a switchboard, for each neighborhood, and everybody can talk to everybody. It's like the equivalent of, a computer switch, where you have, full bisectional bandwidth. But then what happens is, of course, different neighborhoods, they would want to talk to each other. So these guys here, right? Now imagine I just put one switch on top of this here. Then that's really bad, because basically, in the simplest case, if they only really have 3 edges, that means that really only 2 people can talk to each other outside their own neighborhood. And even in the 50s, people didn't think this was particularly acceptable. So what they would do is they would basically add several switches on top, and this way increase the bisectional bandwidth. And you can actually, by clever design, and you can actually make this hierarchical, of course, have very efficient communication structures with pretty good mathematical guarantees. So it's a nice paper worth reading, and a lot of modern switch and network layout infrastructure is essentially inspired by this. Small puzzle for you. Imagine I gave you a switch with only 4 edges. So basically it's a box, and 4 cables come in, and they can all perfectly talk to each other. How can you design a network that will connect all the machines and will give you essentially optimal communication bandwidth between that, possibly with a bit of latency? You have to go through a bunch of switches. So it's a little puzzle. And if you want to know the solution, Google for something called fat trees. And that pretty much tells you already how you might want to design it. But I'm not going to tell you more than that. So think about it yourself. Okay, good. So sorry for diving back deep into switches and network hardware, but it actually sometimes matters to know what your systems run on. Because you can completely trash your algorithm, for instance, by trashing the switch. It's not so hard to do. We've done that. So here's actually what really happens, and this is one way of performing message passing. And this is different from the graphical model style message passing. This is essentially here's what happens. From local to global, you basically just send a diff. You basically just send a message of what locally changed. From global to local, you send the new global state. So now all you have to do is you need basically one extra variable, and conveniently you can actually place that locally, which just keeps track of what the last global consensus view was, because then this way you can also find out what globally changed. And so basically what happens is you receive that global update, you create a local checkpoint, and then you can find out relative to that local checkpoint what locally changed and what globally changed, and you can reconcile this. This is basically one strategy of synchronizing things. So think of it a little bit like when you check into a version control system, maybe you only upload the diff, but then whenever the version control system sends you stuff, it sends you, the full copies. Actually, version control is a little bit smarter than that, but that also means that the server has to do a lot more work. Whereas there, it doesn't have to actually communicate and reason very much with the client of what the client might have. So the good thing is that this works actually whenever the messages that you have are associative and commutative. So in other words, you can reorder sums as they are, and you can regroup them. But it so happens that actually a lot of statistical models satisfy this property. Basically anything that has an exponential family's nature would satisfy this. Okay. So that's how you distribute graphical models. Okay. Now let's look at a slightly more interesting model, namely topic models. So let's start with clustering again. So, there's some web pages about Singapore. Yeah, it's actually a great restaurant. But then, you get a few other things, and, and so now you can argue, well, okay, maybe, these are airlines, universities, and restaurants, right? Fine, you could do that. But maybe you can also group it into countries. And you can argue the toss about which of the two is better. So you could go further and you could basically say, well, hey, this is a US airline, an Australian university, and a Singaporean university, da, 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 da. And so, yeah, that's also a great restaurant, Japanese. But basically, what this tells you is that rather than arguing about which cluster is better, whether my cluster is better than yours, let everybody have their own type of clusters, but basically just call them topics or tags, and you attach them to the objects. So let me show you on another picture. Let's say I have colors. So I could go and cluster the colors by prototypes, and if I have red, green, and blue, then those three clusters will kind of do a decent job, and you could would sort of agree that, yeah, that's maybe kind of okay. But then what do I do with gray, right? Do I have to add yet another cluster here? Well, maybe. And as a matter of fact, on the old 8 and 16-bit displays, that's pretty much what was happening. So does anybody ever remember working on like an X terminal, and if the mouse went out of the window, the entire pictures on the window looked really funky because the colors looked weird? Okay, you're way too young. So basically, this is something that happened very much because essentially the graphics cards could only do 8 or 16-bit of real color representation. So what you would do is, for instance, if you wanted to, have a nice landscape picture, well, you would basically try to find the 2 to the 16 most representative colors in the image. And then there was a color lookup table which mapped this into 24-bit values, and that's what came out of the display afterwards. I mean, by now, of course, that's not an issue anymore. But that basically, you had to run clustering on your graphics card to map into the colors. So the color example that I gave you before isn't terribly contrived. This is actually what was happening. But of course, if your mouse pointer then went out of that image of the beautiful landscape, and you went back to your terminal, which looked nothing like the beautiful landscape, then you needed a different lookup table. And so if the lookup tables were only optimized for each window, it would look really funky otherwise. Now, what you can do instead, and it actually turns out, so I picked those colors to be chosen exactly along those edges with equal weights, so by just messing with the RGB values, you can argue that if I just had a linear combination of those three topics, I could represent my color spectrum a lot better. And if, for instance, you use any color picker, you will probably see something like this, and then also a slider of intensity, quite possibly, to navigate the color space. So what you can see is that basically three intensities will pretty much give you all the colors that you could want, whereas here with clustering, you'll be struggling a lot. So you might need, many thousands, maybe millions of clusters here to represent something that you can represent with three prototypes. Okay. So that's an example where topics can be way more powerful because you can allow for linear combinations. Now, linear combinations are different from not being certain. Sometimes people tell me, yeah, you can actually use clusters, and then you just use the cluster probability. Okay. And that makes a very different inductive assumption on what your data looks like. Imagine you're heading towards a traffic light, right? And traffic lights, have three different colors. I mean, they're either red or yellow or green. And that's just one of those three. They're never a linear combination. You may not be very certain if you're far away whether, it's yellow or red. And maybe you can convince the police officer that, well, you thought it was kind of it's still yellow where it actually was red. But it's almost certainly never the case that the traffic light will display more than one color, at least not in the United States. Right? So what you therefore clearly have is you have a very well-defined state, and there's only really one of three states that the traffic light can be in. But you still may have some uncertainty about whether you saw it correctly because maybe it's really far away. Which is very different from another type of traffic lights, maybe on Mars, where maybe they have different intensities and they fade into each other and do stuff. Right? So in other words, clustering and topic models represent very different assumptions of what our data looks like. Okay, here are both of them in pictures. So clustering basically means I have some cluster probability, then I generate a cluster label, and then I generate my instance. In a topic model, I basically, decide upon, my mixture coefficients, and then for each word, for instance, I pick a topic label, and then I draw an instance. So for documents, you can basically think of a topic model like clustering words within a document, where I decide upon the mixing proportions within the document, one document at a time. Okay. There's another way of viewing it. It's basically you have documents and you essentially perform matrix factorization. This also explains why various factorization approaches to document modeling give you something that doesn't look that terribly different in many cases. So basically, in clustering, this membership matrix just contains a single one and all other zeros. In a topic model, you have a stochastic matrix, so all the probabilities have to add up to 1. For latent semantic indexing, you just have arbitrary matrices. But basically, all three of those methods take the document matrix. So that's basically, number of words occurring in a particular document, which word occurs, and try to factorize it in a lower rank object. Arguably, topic models actually work quite well for that. Here's an example of, document being annotated. This is a great visualization, and you can sort of kind of infer that different colors mean actually different things, which picks it up quite nicely. Now, Gibbs sampling, this is exactly what we talked about before. And in this case, you go and draw, from one variable given the other. And okay, we already saw that in a lot more detail before. But basically, what we have here is the topic probability, the topic label for a particular word. Here's the word. Here's the language model. Here's the language prior. And if you were to sample accordingly, basically you'd sample maybe the topic assignments here, and then you sample, the topic distributions and the language model, basically the word distributions. If you were to alternate this, this would actually work, but it would be excruciatingly slow to mix. Right? you can do it in MapReduce, and people have written papers about, hey, we've solved LDA by doing this. Yes, you found a very fast implementation of an excruciatingly slow converging algorithm. So, by the way, this is another thing to be mindful of. Finding a very fast implementation of a stupid algorithm does not solve big data. I've seen this more often than I would care for, that people go and take a stupid algorithm which just so happens to map nicely to the systems tools that they have at hand, and then they solve this. And while this may be a very impressive systems paper, it's still a stupid algorithm. I mean, okay, you can put rockets on a slug, but it's still a slug. And then that's why then quite often people design more intelligent algorithms, and they manage to beat maybe in single machine implementation a distributed and optimized system. Okay, so anyway, so this is slow, so don't do this. But fortunately, it turns out that you can actually do something much more intelligent, and this is what's called a collapsed sampler. And Griffith and Stivers were the first ones to realize that actually in topic models you can do this very efficiently. More to the point, what they realized is that basically you can integrate out the language model and the topic probability, and you get exactly the expression that we saw before when I talked about collapsed and we only need the counts. So what you need now is you need the counts for the number of occurrences of a particular topic in a particular document, and likewise the number of occurrences of a particular word in a particular topic. Right? So these are basically two count statistics. That's all you need. And then you can sample one of those terms after the other. There's a very cool sampling paper by David Mimno et al., KDD, I think about 3-4 years ago, where they show how you can exploit sparsity in this context. And we actually have a follow-up coming up this year, KDD, which gives you another order of magnitude speed up. But it basically exploits additional structure in these problems to get substantial speed ups. So, in other words, if you can design a more intelligent algorithm that gives you an order of magnitude speed up rather than throwing 10 times as many machines at it, that's always desirable. Because fewer machines mean fewer problems. Okay. So, basically, that's the algorithm. Let's look at the terms here. This is the number of times a particular topic occurs in a particular document. Minus ij means just, well, I'm leaving out the variable zij. So that's basically the jth word in document I. And then I have here the smoother over topics. Here I just need to normalize to make everything sum up to 1. And there I have likewise the same expression. So that's basically for a particular word. So I now need to find out, what's the probability for that word for a particular topic. So I need that count divided by the total number of words occurring in that topic. So that's this term here. And likewise, the smoother. Okay. Bonus question. Which of those terms do I not need to, and mind you, this is not normalized now. I need to normalize it anyway. Bonus question, which of those 4 terms, I have basically 2 numerators, 2 denominators, can I leave out, and the conditional probability P of topic given everything else is unchanged? Okay, so let's just go through it. Let's vote. Who thinks it's this term here? Okay. Who thinks it's this term here in the denominator? Okay. Who thinks it's this term? And who thinks it's that term? Okay. So, well, the majority I think is asleep, but everybody else who voted for this here is exactly right. Because the total number of words in a particular document doesn't change. Yeah, guys, congratulations, you got it right. And yeah, that sum is also constant, so you can actually leave this out. just mentioning this because there's actually an open source version of an LDA code which computes this dutifully at each step. Okay, so don't just copy equations from a paper. Think before you implement. Okay, I'm going to conclude with showing you how to parallelize this. Sorry for going maybe 2-3 more minutes over time. But basically, here's the naive way of doing things. You just do 1,000 Gibbs sample iterations, then you go through each document, then you go through each word for each document. You resample the topic for the word, you lock the topic word table, you update the local table, you update the global table, and you update, and then you unlock. And this is really bad because most of the time, most of the cores will be waiting for somebody. So this kills parallelism. Now, how can we make things more efficient? We basically decouple the global machines and we just synchronize, in a background. Okay. So this gives me multi-machine version, but it's not multi-threaded. So to get multi-threading, we have to be a little bit more clever. What we basically do is we resample and deal with each document locally on each processor core. And then we have a separate updater thread which actually writes. So one thing that we found extremely useful is to decouple sampling from writing. So this way, you only need a lot of read locks, basically threads that only need to read variables, but we know that, oh, great, the JDK wants to update itself. Not now. Great. But basically, we have a lot of sample threads that don't really need to write anything, and then just occasionally one very specialized thread gets to write. And quite often that one update thread that actually writes is enough to keep up with all the samplers. Now let me show you a little bit how this looks like in reality. This is log likelihood for running on 6,000 computers, and this is basically, as a function of runtime. This is stratified over iteration count. And here are convergences. This is on 500 million documents on 1,000 and 6,000 machines respectively. And you can see 6,000 machines are faster than 1,000 machines, which is good. So just to put this a little bit, so these are experiments that were done at Google. Just to put this a little bit into relation, this is the largest nuclear reactor in the United States. It produces 3 gigawatt. Okay. One machine is about 10 cores. One core uses probably around 50 watt. So we used about 3 megawatt. So it was basically 0.1% of a nuclear reactor that we were burning for our experiments. After that, my manager at Google came up to me and said, Alex, this was an expensive experiment. I hope it was useful. It actually is. Let me just conclude with 2-3 minutes about user profiling. This is how people sometimes like to do user profiling, especially if you go to the touchy-feely kind of people. They like to actually produce such stuff a lot. I hate it. Don't do that. Here's what you do instead. Let's say you're in the market of buying a camera. You go and search for stuff. And, well, okay, sorry, I clicked a little bit too fast, but this already takes things away. This is still back in the old days when we were all at Yahoo. So this is when I think about buying a camera. This is when I start searching for it. Now I've bought it. This used to be a really good camera at the time, by the way. But basically, if I show you the ads here, it's too late. Maybe I can sell you a memory card, but if I show you another ad about, hey, by the way, would you like to buy this LX5 for $430, I'll just be frustrated. It doesn't really help. So you want to pick up really early on when somebody's in the market of buying this. Here's the statistical model that we saw already before. Basically, rather than documents, we now have users. Rather than words, we have user actions. And everything is time dependent, and don't worry about the rest. But I'll just conclude with those pictures. So these are some real users. I don't know what their gender is. But here's some topics. The only manual thing that we did is we gave them names. And I think you would agree that women, men, dating, singles, personal, seeking, match, it's probably aptly named as dating, right? And so, well, there's this first user who is arguably interested in dating. Then at some point, he starts worrying about his health, God knows why. And then, okay, dating takes a bit of a dive. Then he discovers baseball, and at that time, dating's not so interesting anymore. This guy's a diehard baseball fan. At some point, he realizes he doesn't have much money. And about, 2 weeks later, he starts looking for jobs. All the way, dating's really not so exciting. So these are real users. Now, why do you care? Well, you see those 3 red circles. This is when I can show you ads when they're going to really work out, right? Because, hey, would you like some baseball tickets? Yeah, by the way, here's some ad for Bank of America. And by the way, LinkedIn has a new profile for you that you want to try out, right? It actually translates into money. These were slightly smaller experiments. We ran it only on 1,000 machines, but also about 500 million users. And yeah, it helps. And this is all I wanted to say today. Tomorrow, we'll look at hash kernels and other fast data structures.